So we are considering tabular data that is stored in data frames, and in particular, this data is multimodal data. And that belongs to the arena or domain that's called multivariate statistics. And with this in mind, there are specifically for the features or columns that are considered numerical statistical variables, there may be some association or dependence between those features. And so you may address this by considering groups of 2 features at a time and then exploring if there is a visual diagnostic would be to create a scatter plot of one of these columns versus the other one. But you could also compute these so-called correlation coefficients. In a nutshell, is as if you are assuming or exploring one column against the other one, and then you're also exploring some type of slope, as if you're assuming that the underlying model is describing a linear relationship. And if it were linear, what would be the slope of a line that best fit all the points displayed on this plane that contains these two variables. So for the correlation coefficient, what you see here on the left side, it's very important to remember, we're still assuming that df is the name of the variable stored in the data frame. And just as far as syntax, very important to remember here that you are specifying, we're considering 2 features at a time, but you're specifying the names of those columns. But very important, just look at the syntax here. This is enclosed with double square brackets. Okay, so it's the opening and ending. There is double square brackets over there, and then the method that's used here is like the short of correlation. So it should be a straightforward method to remember. Now, the method for creating a scatter plot. This is a combination of using both pandas and matplotlib. And so here you see basically a concatenation of plot and scatter, and then the input here are the 2 columns. So we're exploring 2 possibilities. On the right hand side, we see we're looking at 2 variables. One is one feature, weight versus height, and then we see a clear correlation, and also would like to think that these data points here depicted as solid circles, that these data points are aligning well in the shape of a line, and specifically this would be aligned with a positive slope. So you may create this mental picture that slope, if we assume that the relationship is linear between the 2 features under consideration, the slope is almost analogous to the so-called correlation coefficient. There are some technical details that they're not exactly the same, but they're very similar. When there is a positive slope, there is a positive correlation coefficient, and when there is a negative slope, then there's a negative correlation coefficient. When 2 variables like weight and height here have this positive correlation, that means very clearly when you increase height, so you want to consider this on the terms of the independent variable that's on the horizontal axis. If you increase height, then that will give you an increase on the dependent variable, which here would be weight. In contrast, what you see here on the left hand side is a scatter plot of 2 variables that are not correlated. There's not a linear shape with either positive or negative slope. Instead, the points seem to accumulate almost like a giant circle over there. And you would say that this is actually not exactly like a pattern. This would not be considered a pattern. When you're looking for patterns, it's like you're looking for lines, parabolas, maybe something similar to a polynomial of degree 3 or higher, sine, cosine, something that it has some type of shape. This is not exactly what you would call a shape that describes how one variable depends on the other one. So correlation coefficients, I said, they can be analogous to a slope. Usually in general, slopes of lines are not bounded. They can take any value from negative infinity to positive infinity, but correlation coefficients are bounded. They are between the interval -1 to 1. So they may be exactly equal to -1, they may be exactly equal to +1, and then they may take values in between, particularly the value of 0. So when you have correlation estimates for the correlation coefficient to be close to 0, either from below or from above, but close, approaching 0, that means that's a good signature or footprint that there is no, the correlation between the two variables is really, really weak. You could say there is no correlation. And when those values of correlation approach either of the lower bound or upper bound, then you can say that there is a really strong correlation, either in a negative sense, if it's close to -1, or in a positive sense, if it's close to +1. So you may actually store this considering more than two variables at a time, and store this in a matrix that's called a correlation matrix. And you would, what you're seeing right now on the screen is the syntax for the method here. The method that you would use is this method where you can, here is illustrated with only two columns, so you can actually add more columns, and therefore this will give you, the output of this method will give you a matrix that has the correlation coefficients across the considered columns or features. It is also common to read these correlation matrices with yet a visualization, another visualization, which is called heat map, in which you have a color code. You're trying to distinguish between values of 0, values of -1, values of +1. So the heat maps are useful for color coding certain regions, and it gives you a nice visual diagnostic for determining the dependencies between across features or columns. So this is in relation to the plot that we had seen before, where on the left we had something that had very poor shape, very poor correlation, so that corresponds to the feature called H and the feature called number of classes. What you're seeing here in this table under name, basically feature 1 corresponds to H and feature 2 corresponds to number of classes, and we're seeing that it is approximately, the correlation here is positive, but is approximately 0.013. So this would be considered poor correlation, or correlation close to 0. For the other two features, height and weight, this table lists here in the name feature 1. Feature 1 means height, and feature 2 means weight. That's what is meant here. This is supposed to be weight, and feature 1 is supposed to be height. Okay, and so you see that there is a correlation that's positive, and it's, in this case, this is what we would consider to being closer to 1, and because it's approaching 1, then this resembles having a positive slope. So it is important to determine if columns or features are correlated, because this may interfere with the performance of machine learning models or algorithms. And we would prefer to identify ahead of time which columns correlate with one another, to then maybe simplify the problem in the sense of, it's like throwing out redundancies and only keeping a subset of the columns that we would consider active for the machine learning algorithm or model, a subset in which the features are not correlated to each other. So this would give us maybe simpler models, which are constructed on fewer features or in a subset of the original features. And in a way that one value of this simplicity is that they tend to be a little more accessible to interpret or to implement. So in other words, when we identify columns or features that are correlated or highly correlated, we may engage in dropping, so making the decision to drop some of these features or to fix them. Well, maybe dropping is a better term. And anyway, dropping some of the features would mean that the model may be seeing improvements in terms of training speed. This is also something called reducing the dimensionality of the model, because in a way you're kind of reducing the number of parameters. So one thing to keep in mind is when features are correlated, those that we decide to exclude are not really very informative to begin with. And so there may not really be a terrible consequence by dropping these features, because they're not really providing meaningful information. In a sense, that's the redundancy. And so on the other hand, features that are highly target correlated, they might improve the performance of some of the regression models.